Perfect. Hello, everyone. Good morning, good afternoon, good evening. I know that we are at different timetables, so hello to all of you. Okay, Marcos has already presented me and the title of the presentation. So let's start it. Okay, as all of you know, Miridae is one of the most diverse, one of the 20th most diverse family of insects and the most diverse family of Heteroptera, with more than 11,000 species. They are known from all biogeographic regions, and there are 7 subfamilies recognized worldwide. The fourth subfamily in number of species is Bryocorinae, which has an astonishing morphological, evolutionary, and ecological diversity. And the classification of this subfamily has changed over time, and a recent phylogenetic analysis recognized 5 tribes. So we have here Bryocorinae, Discipini, Felicacini, Monolocorini, and the most diverse and numerous Eccritotarsini. These tribes has a great morphological variability that includes size, coloration, appearance, as you can see in the pictures, and even male genitalia. For most of the species, the host plant haven't been recorded, but for the ones they are, at least in more than 60%, they are monocots, which is different from the rest of the mirids. And we have that many species are important plant pests in this tribe. During my PhD thesis, I studied a genera complex that include 5 Eccritotarsan genera and its species, and I faced some issues that I'm going to mention. Most of the species were only known from their original descriptions. Of course, there were many species that were mentioned in regional catalogs, but most of them for distributional purposes. The original descriptions are short and focus on coloration, and also in the museum collections, there are few specimens, and most of them, the specimens from different species, are mixed. That is not only for general collection, but also for type specimens. So a lot of nomenclatural decisions had to be taken, like, for example, lexotype designation, synonymization of the species, and what is also related with the next topic that many tribes are destroyed, also neotype designation. Like, for example, this is a paper I published with my directors a few years ago, where we redescribed one of the genera I studied, Paraneella, and also we designate a neotype that is, till now, the only known specimen of that species and genera. Maybe some of you remember my presentation in the last meeting in Spain, where I show you the preliminary results of my phylogenetic analysis. There you have a picture of the talk, and also some macroecological studies I've done related to ecological niche models. The results of that macroecological part of my thesis are not published yet, but I've been working with those tools, for example, in this paper published 2 years ago, about Pycnoderus quadrimaculatus, that is an Eccritotarsan species known because it is an important plant pest in all America. And also this one that is new, about a discipline species, Minghetti passionarius, that is a potential biocontrol agent of Passiflora foetida in Australia. In these 2 papers, you are going to see the macroecological tools I use also in my thesis. But today, I want to present you the final results of my phylogenetic analysis that are going to be published soon, I hope. And that analysis is based in morphological characters, and many of the characters I use are novel ones. Today, I'm going to show you just the ones related to male genitalia. So, For the phylogenetic analysis, I studied the specimens deposited in museum collections, and I also saw a photograph of many type specimens, the ones I couldn't see face to face, let's say. I used the software TNT, and a total of 52 terminal taxa were used, an in-group that included 45 species. 5 species were not included because I couldn't see material or the photograph wasn't good enough in order to relieve characters, and the outgroup includes 7 species, 6 Eccritotarsini and 1 discipline, the one I mentioned before, Minghetti passionarius, to root the tree. So I used 160 characters, 20 continuous that were treated as additive and rescaled to units in order to reduce the effect of larger characters on the matrix, and the rest discrete between multi-state, a few, and most of them binary, all treated as non-additive. Both kind of characters, continuous and discrete, were described as well as their state following Serenos paper. Missing entries, that means characters unable to observe, were indicated on the matrix with the question marks, and inapplicable characters, especially in this group where I had a lot of sexual dimorphism, were treated as such. That means that the hierarchy of the characters were imbibed at the end of the matrix with characters and state names. I'm going to show you that in a few minutes. That allows TNT to assign appropriate transformation codes to each character. So here you have an example. This is a part of a matrix where you have the continuous characters, and here a part where you have the discrete characters. Till now is a normal matrix. But at the end of the matrix, under the command for TNT, where you indicate the names of the characters, you have the number of the character, the name, separated each word with an underscore, and then separated by spaces, the states of that character. If you look at characters 23 and 24, they are different from the rest. That is because they are inapplicable. So, character 23 is related to eyes stellated, and it is an inapplicable character, and that is indicated with a prefix before the name of the character, that is sub, which means superior. Then we have the states of the characters that always has to be absent and present. And then we have the subordinary character, because I want to characterize that, that eyes stellated, where they were projected laterally, anteriorly, posteriorly. So I indicate this with another prefix before the name of the characters that means subordinary. And then I have the name of the character and the states I need it. In this case, you can have as many as you need. But it should be taken in mind that there is a limit of the total number of states you can use when you work with these kind of characters that you can't pass. For the rest of the analysis, I use implied weighting as it outperforms equal weights with concave values that varies between 8 and 12 as they are recommended. I perform an heuristic search, and here you can have the parameters of searching, and I calculated the consistency and pretension index for the trees. I found one tree for each concave value, and the trees didn't vary between them, only the position of the outgroup changes, and in some cases, the relation of the genera also changed, but not the ones that were my in-group. And of course, the species included in each genera stay constant in the different trees. I choose one tree to show you the results. That is the tree found with a concave function value of 8 And here you have the length, the consistency index, and the retention index. I'm going to show you the picture of the tree divided in two because it is too large to show in once and you are not going to see the names. So here it is, the first half of the tree. I mark here part of the in-group genera that I was studying. This is a known genera, Annela, that has many species transferred to it as a result of this analysis. Here you have Paraneella, and this is a new genera that is going to be published with the results of this analysis because the species that are included were originally described in another genera. And here I highlight the novel characters I'm going to show you in a few minutes, in order you can see where they are distributed in the tree, in the genera, in the species. So here we have the other half of the tree, and the same. I mark this is Proneella. Here we have Neonella. These two genera are known, and they have no changes in their composition as a result of this analysis. And this is the other known genera, Neella, that is the one that has most changes because many of the species that were included were transferred to known genera or new genera. And here we have all the others that are marked here are new genera. We have all that are include the light blue, the yellow, this pink, and this brown include species of Neella. But the red one is a new genera, a new genus, sorry, that we published last month, all with new species. These new species were originally mixed with specimens of Neella, Neonella, Proneella. They were in all over the genera I was studying. And in this paper, you are going to see many of the novel characters used and that I'm going to show you just right now. Here, they are highlighted for this half of the tree. But what are these characters about, where they are related to? They are structures of male genitalia that I found when I was doing the dissections. I looked for information in papers and I found that they were poorly mentioned and illustrated in papers. Maybe you can find that some author says that these kind of structures were present, but you have no characteristics, no information about the position or location, nothing. There is a paper of Katrina and Tom where they use these kind of structures in new genera of Eccritotarsine species they describe and they use to relate genera. So apart from that, we have no more information. So I found that at least in these Eccritotarsine genera and species, we have projections of the genital capsule. They are all external in this case, and I'm going to show you some examples with pictures. This is a new genus that has this pretty big projection in the left margin that is very characteristic. You can see it from without dissecting the abdomen in a lateral view, so it's easily to recognize the species of this genus. Then we have, this is one species of Heteroptera, for example, that has this smaller projection also in the left corner of the dorsal margin. For Neella species, instead of having dorsal projections, we have posterior ones. Here in these two species, you can see a left one, but it can be in the right side, in the left, and in the right, one larger than the other, of equal size, that varies between species. For Neonella species, we have a dorsal projection, but in the right corner. And finally, for Proneella species, we also have a left and dorsal projection, that, as well as in this new genus, under the projection, it is a concavity where the apex of the right paramer is located. So in a resting position, the right paramer crosses completely the genital aperture and goes right here. Then we have another kind of projections that are the projections of the subgenital blade. The subgenital blade, in order, if you don't know where it is inside the genital capsule in the floor, and it is an sclerotization where the edeavos is located. When I do the dissections, the first one of this species, I had to break the genital capsule to remove the edeavos because it is like glued to the floor, so it is really difficult to remove it. And for the way I have to break, or I used to break the genital capsule, when I remove the edeavos, I remove it with this kind of projections. For some species, I changed the way I break the genital capsule, and I saw that surrounding the edeavos, they were projections that came from the floor of the subgenital blade. So I remove it very carefully, and I can describe and illustrate this kind of projection, and that is I'm going to show you right now. For this new genus, we have that these projections are in the right part, and they are completely inside the genital capsule. For a Heteroptera species, here you have a picture of each species, you can see that we have left and right projections, and both of them goes out the genital capsule. So you can see them from the outside. Of course, here the parameters are removed, but in this species, when you have the parameters, the right and the left, they are like surrounding this structure. So maybe it is difficult to understand what part is subgenital blade, what part is the parameters, especially in Eccritotarsini, where parameters are asymmetrical and sometimes really complex. But it's just to remove them and you can see this kind of structures. For Neotropical species, we have also right projections inside, and here you have a picture of what happened with the first dissections I did. I removed the edeavos with part of the projections that are marked here. So you need to remove it really carefully to show where they came from and where they are located and the shape of these projections inside the genital capsule. Lastly, I want to show you this new genus that has a huge right projection of the subgenital blade, that is this one here and this one here. In these two pictures, the right parameter is removed, but it should goes here and here. These projections move from the inside to the lateral wall, the right wall, and then it closes dorsally the roof of the genital capsule that is reduced. So in a lateral view of the abdomen without dissecting, or in a posterior view, you can see this structure that is like surrounding completely the right parameter. To sum up and conclude this talk, I want to highlight that these kind of structures prove to be really useful for characterize and diagnose species and genera. And as you saw in the phylogenetic analysis, they bring important information about relationship of species and genera. I think that at least for Eccritotarsini species, we need to take this into account in order to describe this kind of structure, photograph or illustrate them, and also use them in the, or look for it in the known specimen, known species, and also for the new ones, so you can understand where they are distributed in the tribe and use them in future phylogenetic analysis. So I hope you have enjoyed this talk, you find it useful, and of course, if you have any question, I'm glad to answer.